So thank you to the speakers again. Adam, you did a nice overview, I think, of this, the area of prediction and stuff, and that was pretty much, most of my comments were about the electome voting behavior for mice or something. So I think I'll just skip those, and we can go straight to questions. So if you guys want to have a seat. We'll get that started. So I think that the prospect of prediction, especially in this day and age when we have so much data and there are so many questions that for the first time we might have the means to answer, is very exciting. But as a scientist, often what we are trying to do is explain things, explain mechanisms, understand why something is happening, with the idea that if we can explain something, then we can then predict across many different contexts in a more generalizable way. I think one thing that's become clear is over the last decade that prediction can far outpace explanation in certain areas, right? So you think about Amazon and Facebook and Google and how well, I started to use the word y'all recently, because as an alternative to you guys, because maybe that's a bit gendered or something. And I feel like I haven't actually implemented this intention on my phone, but my phone's now auto-correcting to y'all. Like, just random words get turned into y'all. And that's amazing to me. Like, I didn't even form the intention yet, and my phone seems to already know. That was a tangent. The tension between prediction and explanation, though, what do you think about this? Like, should we abandon explanation because we have the data to predict and we don't need it anymore? Or is there a way in which we really need to sort of rein in some of our potential predictive power, because prediction can go wrong and explanation is still at the root of science? So maybe maybe you can start.
Yeah, so I'm a basic neuroscientist, so understanding is really important to me, right? So I think there's a lot of utility to predicting, but if the ultimate goal is prevention, then you need to hopefully predict something that is related to biology that you can intervene on, right? And so in that case, we need to move beyond the step of predicting, and get to an understanding of the underlying processes, right? So it has to be interpretable. So for us, we're even thinking about, if at a minimum we have a predictive signature, can we then use that to segregate animals into groups, right? The high-risk group and the low-risk group, and ask what is different about those groups that we can then intervene upon. But we don't want it to just stop at the ability to segregate animals.
Yeah, I mean, I go back and forth on this because I feel like we spent a lot of the last 20 years, let's say, trying to use neuroimaging, as an example, to better understand circuits in the brain, and it hasn't really panned out in terms of a useful predictive tool. And so I guess, whereas like I think, we might be able to use something like resting state functional imaging to predict something useful, even if it doesn't actually help us get that much at underlying biology. But I do agree, like if we're going to get clinicians using AI, any kind of algorithms to guide care, just like an EKG, I'm sure when cardiologists first started using EKGs, there's a lot of skepticism on the part of people who were used to just listening to heart sounds. It took sort of a coherence of those signals that the experts could listen, and it matched up with what the EKG report was showing and suggesting that over time lent itself to an explanation. In other words, we can use different types of language to come at the same concept, and they're parsimonious. So I think it doesn't have to match perfectly. I mean, humans, we are always happy to kind of fill in gaps that don't make perfect sense, as long as it's in general pointing us in the right direction. I think as a clinical pragmatic issue, I think we would be happy with prediction, but if it doesn't align with clinicians' intuition, no one's going to really use it, I think.
Yeah, and I don't have too much more to add, but just that as we've been talking about, trying to have them go forward in parallel as opposed to opposing each other, and I think particularly in the near-term prediction, without real understanding, can make progress while we get to the actual biology underlying it, and develop new treatments and interventions based on that.
So in the description of this panel at the end, it said that one of the goals was to talk about what's going to be possible in the next 2 to 5 years. So I don't think I heard any concrete predictions about the next 2 to 5 years. So any bookies in the audience? No, probably not. It's probably a good thing, honestly. No bookies in the audience. if you had to make a prediction, let's say 5 years, because that seems more room for error, right? In the next 5 years, if you had to make a prediction about what's going to be possible that isn't possible now, what would it be? And if you're wrong, you won't be invited in 5 years if you have to come once again. So, Adam, I don't know if you want to start here. No? No? Okay. Anyone? Yeah? You want to try?
I would love it if we're doing PHQ-9s routinely. Yeah, that was my safe bet.
Yeah, so funny enough, I'm actually wrestling with this question right now. So I'm part of the advisory committee for the BRAIN Initiative and the 2.0 version. So BRAIN Initiative was launched in 2013 with the goal of understanding how the brain works, right? With the long-term goal to come up with new tools and technologies that we can apply to understand the human brain and ultimately treat disease in the long run. And so we're about 5 years in, right? So we're doing our halfway evaluation point, and we're supposed to come up with our thoughts on what's going to happen in the next 5 years. So this is exactly this sort of thing that we're wrestling with now. And my hope is that we'll have tools that will enable us to quantify activity in the human brain in a new way in the next 5 years, right? A lot of our early advances have been taking advantage of the fact that when we do neurosurgery with deep brain stimulation for things like Parkinson's disease, so we have ways to record activity in humans. I actually had a great conversation with a neurosurgeon. Turns out, when you're doing these implantations, you're actually like removing brain tissue that we don't then do things with, right? So we're like, there are tons of these deep brain stimulation surgeries going on. We're removing human brain tissue, and then we're not asking questions about how the human brain is organized. So in 5 years, I'd love for us to start doing more of that and to figure out how to connect our model species better to the human brain, right? I think the pathway to translation is much easier with other organs than it is the brain, because we certainly don't transplant human brains, right? So you need it, right? It's fundamentally who we are, so we don't go, biopsying it all the time. So that's my hope for the types of things that we'll see in the next 5 years, new technologies that allow us to get a cleaner understanding of how the model species relate to the human brain, and that'll serve as a platform to come up with new treatments for disease.
And I think sort of in a more mundane way, I think there's, as Adam highlighted, there's a lot of stuff out there that we know that's beyond the testing phase that we know work well, like feeding back data to clinicians and doing routine PHQ-9s and some mobile interventions. And I think and hope in 5 years we'll make real progress in getting that more broadly used in both routine clinical care and more in the prevention of the onset of depression and other disorders.
Yeah, I guess I'm struck by the fact that, kind of like cardiology, it's really only recently that we've started measuring behavior in humans. And by that I mean actually measuring temporally dense behavior in natural settings and that sort of thing. It's sort of my expectation that once we've looked at behavior, the properties of behavior as a dynamic system isn't really going to be any different qualitatively than a lot of other dynamic systems that, whether it's weather or the heart, or, I think once we've looked at it and there's actually a growing, the communities like this collecting these samples, we're going to learn a lot about how humans work, and we're going to actually, once it's just kind of routine to not just observe patients in clinical settings, but to actually measure things about them, that the field's going to change. Now, I don't know if that's going to happen in 2 years or 5 years, but to me, it's just a matter of, once you flip on the switch and you begin measuring things and quantifying things, I feel like we'll probably mature our science somewhat quickly. Again, this maybe is a hope, but maybe a prediction. But I think the other piece of that, in terms of thinking about what some of the device makers and the operating system makers, some of which are here in the audience, just like you mentioned with your phone starting to kind of predict your own behavior, I'm excited by the prospect that within a few years, it hopefully will be commonplace that our devices can give us helpful nudges towards, our own performance optimization, whether it's, helping us get better sleep or helping us not notice the patterns that, for us individually, predict mood alterations, things like that. So I feel like, academics are slow. We have, we're going to be collecting 100 people over the next 4 years. Apple, Google, these other companies, they're going to collect millions of people. So I think I'm optimistic that the more, I think Guillermo mentioned in his talk about psychiatry actually helping inform the development of those technologies. That's, to me, what's most exciting in some ways, because I think the technologies are there, we're all using them, but how those software that's in those technologies helps us in a way that's informed by, the fields of psychiatry and psychology, to me is what's most exciting.
Any questions from the audience?
It was a great panel. And Justin, I really like your final statements. That's what I was thinking for the next 5 years. And Srijan, am I saying your name correctly? What I'm hoping for is the same kind of closed loop feedback that Justin mentioned for the data that you're collecting could be used profitably by the training directors where, sort of in real time they get some kind of aggregate feedback. So they can't identify, who's the person, but so that they can adapt their programs and that there are consequences for them if they do not. But so that kind of closed loop feedback treatment I'd like to see happen with the training system.
Yeah, I think something like that would be great. I think we've been focused on getting the feedback back to the individual because that doesn't have as much of the private. These guys are my clinical work is treating the residents who are depressed, and there's so much stigma and paranoia about what their training director will find out about the session, what they think. So trying to find a way to get data to the training directors, institutions in a way that that the individuals feel okay about is a challenge. But I agree something like that would be great in an aggregate way.
Because a lot of the risk factors you identified are structural and beyond the control of the trainee.
Yeah, right. A lot of the variance is at the level of the program and even more at the level of the institution, and trying to make change at those levels, both in this specific population, but hopefully it's a representative of broader problems that we can address.
Yeah, so I guess I have two quick questions. This was an awesome panel too, by the way. I guess the first is, how do you audit these, the results of these algorithms to ensure that certain groups are not consistently having negative consequences? So, you talk about like 8% prediction rates and things, but like, certain comorbidities having more risks and things like that. So that's one question. And the other one is getting back to the idea of Google and Apple having millions of users, and a lot of researchers here who don't have the technical capacity to do the types of analyses that, like the voice analysis that you're doing. Is there a way that we can build tools that allow researchers who don't have the technical capacity to still like give the audio from their studies, and which would help improve the algorithms, but also increase access to better technology and algorithms for those researchers as well?
I mean, on the last point, we've been working to try to develop platforms that will make it a much lower barrier to entry for people who are already working in more analog ways, whether it's conventional patient interviews to acquire, a clinical scale, or interested in, ecological monetary assessment, but wanting to get more into passive sensors from phones. So these tools are out there. So BWE is a tool that was mentioned yesterday. JP Onella's group has built that. It's openly available now, so really anyone with some technical expertise can at least, if you have it at your institution, can get that platform going. And then we've been building tools to try to help people make sense of the data, so not just acquiring it, but having data from different sources, whether it's surveys or Twitter or things to kind of get aggregated and be able to make more sense of it. So.
Yeah, and I think you're making an important point that it's sometimes lost on us, right? So it's this idea of generalization, and if you think of even the intern class of, the intern class that comes in, that class probably doesn't generalize to the rest of the population, right? So we might learn things that are absolutely true of that population that then doesn't tell us about the rest of the United States, it doesn't tell us about lawyers, and even our genetic databases don't necessarily tell us about other parts of the world that are not included in the genetics databases that we're using to find those risk signatures. So I think having platforms where we can get information quickly from many sources into the same spot and built into the models are going to be really important for coming up with understanding that then generalizes across populations. So thanks for making that point.
And just specifically on that, our genomic risk score had a pretty good predictive value, but only in Caucasian interns. It had no predictive value in other races.
I would also just say your intuition is kind of right on the first point as well. There are software engineering frameworks that apply when you put a machine learning model into production. You will usually put safeguards around that, so you monitor over time, for example, the distributions of the predictions that go through. You can break down the distributions, according to age, race, gender. You always would, try and loop back outcomes and test models before you, before you update any algorithms. You will back test them and make sure that they work. So the things that you just kind of touched upon are pretty accurate intuitions of how test-driven development works.
I think we have time for one more question. I know you've been waiting.
Thank you. So it's all very interesting about the digital phenotyping or the temporally dense behavioral data, but I wanted to hear your thoughts about how we can extrapolate to what's happening in the brain in relation to those this digital phenotyping or dense temporal behavioral phenotyping.
Sure. Right, so I think part of this is, well, I'll answer this in a funny way, right? So I think it depends on what brain you're interested in, right? Whether it's a model organism or a human. Ultimately we need to extract information out of the human brain in a reliable way. It doesn't need to be perfect signals, right? You could imagine everyone sleeps with a ball cap on their head that extracts EEG while we're constantly monitoring behavior as people are moving around. I don't know what that technology is going to be in the long run, but we do need some way of measuring brain activity quickly and cheaply that then scales across a population to match with the behavioral data. And if I can actually just make one more comment. We talk about this is a technology conference, right? So we talk about high-tech stuff all the time. But I don't want to miss out on that some of the things that we learn that is actually interpretable has low-tech solutions, right? So for us, we're finding these risk signatures that are showing up in animals exposed to early life stress. And clearly one of the things we need to do is figure out how to take better care of babies, right? And that will decrease risk in adulthood as well. So, it's not just discovering these things and figuring out how to predict and which parts we can intervene on. It's actually building systems that allow us to implement this, right? So even thinking about interns, we have to build systems that allow us to then implement the information, or we're just doing really, really cool science experiments.
Yeah, just to follow up on the question, I mean, the way we were thinking about this is to try to measure human brains over time, but to capture them when they're in different mental states. And at least with that, you have the opportunity to kind of capture that same individual as they enter different mental states, depressed, manic, euthymic, and then just ask the question, is there a way to kind of, knowing from all the available sources, their own self-report, clinician report, whatever their digital phenotype suggests, and whatever their brain image is showing, is there a coherent motif there that we can detect, and is it really reproducible that each time that person goes into that state, are we seeing the same pattern of sensors and brain imaging changes occurring? Because it might happen once, but I think we want to see reproducible, correlation. And then just one example of where we're fortunate to have in opportunistic studies where people do have like deep brain stimulation electrodes in place, and in some cases where you can even record from neural activity from humans while they're just going about their daily lives. And so we're currently working with Darren Doherty's group at MGH, where they're doing some deep brain stimulation and recording in a select group of treatment-resistant patients. And so in that study, the NIH basically asked us to add on these sort of temporally dense behavioral sampling because they're spending so much money, to put this really fancy technology into the brain, and the readout is, how's the last couple of weeks been for you? So I think that at least kind of bringing temporally dense behavior into the conversation where, there's a lot of money in Brain Initiative, for instance, that is going to developing the new tools.
Thanks again to our speakers, and Carrie Resler. Oh, there you are.